So we have already introduced the notion of non-homogeneous Poisson process as an extension of a homogeneous Poisson process. So a natural question that arises is how do non-homogeneous Poisson process actually arise? Let's say we accept that homogeneous Poisson processes do come up in applications, but how do non-homogeneous Poisson processes arise? So main aim is to show two different ways in which non-homogeneous Poisson processes may arise from a homogeneous Poisson process. In this particular module, what we are going to show is one of those ways is start with a homogeneous Poisson process and then look at what is called a time change of this homogeneous Poisson process. In other words, what it means is, so the homogeneous process is indexed by time t. So t is the natural time of the process, but instead of observing this process along that natural time scale or natural clock, look at observe the same Poisson process but in a different changed time clock. It could be observing nt at not at time t but t square, and so on and so forth. So these are typically what are called time changes, and one way to get hold of a non-homogeneous Poisson process starting from a homogeneous Poisson process is by observing such time change homogeneous Poisson processes. So this is what we'll explore, and then we'll also see whether we can get back from a homogeneous Poisson process. When can we get back by possibly a reverse time change to the original homogeneous Poisson process? So we continue with non-homogeneous Poisson process. Let's quickly recall the definition. Counting process nt with independent increments and starting at 0, that means n0 is identically 0, such that the increment nt minus ns for any s less than t is a Poisson random variable with parameter which is the integral s to t of lambda u du is called a non-homogeneous Poisson process with rate intensity function lambda. Of course, this is not how we originally defined non-homogeneous Poisson process. We defined it to something else, but then we saw that this is an alternative equivalent definition. So that's what I say next, that is, this definition is equivalent to saying that nt is a counting process with independent increments and n0 identically equal to 0, which satisfies this infinitesimal conditions. So small interval t to t plus h, the probability of there being 0 arrival, 1 arrival, and 2 or more arrivals. Now, to get a somewhat clearer understanding of non-homogeneous Poisson processes and how they actually occur in practice, because we have by now a somewhat clear picture of homogeneous Poisson process, how they occur through exponential waiting times, etc., etc. So here, let's try to see how they actually may occur in practice. So we'll describe two different ways in which a non-homogeneous process may arise out of homogeneous Poisson process. So we are basically assuming that homogeneous Poisson processes do arise in practice. Now so we accept that. Now we are going to say out of homogeneous Poisson process, how one can suddenly come with a non-homogeneous Poisson process. So first method is NHPP through a time chain of a PP lambda. So let's understand this. So essentially, you run a homogeneous Poisson process, but run it in a different time clock. We'll explain what it means. So starting with a homogeneous Poisson process nt, but then observing it in a different time clock in one way is one way how one can get a non-homogeneous Poisson process. So let's start with an example. Let nt be homogeneous pp lambda. Define n tilde t to be n not at t but n at t square for t greater than or equal to 0. Then you agree that n tilde t is a process defined for all t greater than or equal to 0. It's also clear that n tilde t is a counting process, because again it would be increasing with t through step paths, and each time there is a jump of size 1 starting from 0 and increasing by jumps of size 1. So it's a counting process, and n tilde 0 is 0. Further, for any s less than t, if you look at the increment n tilde t minus n tilde s, which happens to be the same as original nt square minus ns square, but by the fact that n is a pp lambda, we know that nt square minus ns square is the increment of the n process over the interval s square to t square. That, of course, is Poisson with parameter lambda into t square minus s square. Now notice that lambda into t square minus s square is the integral of 2 lambda integral s to t u du. So it follows that n tilde t minus ns tilde is Poisson, but the parameter is integral s to t of 2 lambda u du. So what it means is that n tilde t is a non-homogeneous Poisson process with rate function lambda t equal to 2 lambda t. Essentially note that what is n tilde t? It is nothing but, it is turning out to be a non-homogeneous Poisson process, but it's nothing but the original homogeneous process nt, but observed in a different time clock, namely the t square clock instead of its natural t clock. In general, let capital lambda from close 0 to infinity to close 0 to infinity be any function with, first of all, lambda 0 equal to 0, and 2, having a non-constant continuous derivative lambda t equal to capital lambda prime t positive, which would imply that capital lambda is strictly increasing. Then the time change process, namely n tilde t equal to n at lambda t, as you know, for t greater than or equal to 0, can be easily seen as a counting process, and one can actually see that it's a non-homogeneous Poisson process with intensity function lambda t. You can proceed exactly the same way, because the increment, it would be a counting process, would have independent increments, because capital lambda t is strictly increasing, so this would have independent increments. It will start at 0, and now when you look at the increment of n tilde process, n tilde t minus n tilde s, that will be n of capital lambda t minus n of capital lambda s. That has a distribution lambda into capital lambda t minus lambda s. So therefore it's just a matter of writing that as an integral of a function, and since capital lambda is assumed to have a continuous derivative, you can write the increment of capital lambda t minus capital lambda s as the integral from s to t of little lambda u du. So that's how the intensity function comes into play. Notice that the n tilde process is nothing but the n process, but observed in the lambda t time clock rather than t time clock. So this shows how a non-homogeneous process may arise as a time change of a homogeneous process. Okay, so you change the clock of the homogeneous process. Originally you have a homogeneous Poisson process, but then you rather than instead of looking it along the time clock t, natural time clock t, you look at the homogeneous Poisson process in a different time clock. So that's a time change, and often such time changes, appropriate time changes, give rise to non-homogeneous Poisson process. In fact, this above actually shows, even if you are required to construct a non-homogeneous Poisson process with a given rate function, how you can do that. So here is how it goes. Suppose you are given a locally integrable function lambda from positive reals to positive reals. So use capital lambda t equal to 0 to t lambda s ds as a time change. Notice that this capital lambda would satisfy all the conditions, namely capital lambda 0 is 0, and capital lambda has a derivative which is little lambda, which is given to be strictly positive. So therefore capital lambda is strictly increasing. So you can legitimately use this as a time change on a homogeneous Poisson process with rate lambda, and that will give you a non-homogeneous Poisson process n tilde t, which is n observed at capital lambda t, whose intensity function would be the given function little lambda. So given any locally integrable function, you can construct a non-homogeneous Poisson process with that as the intensity function simply by starting with a homogeneous Poisson process with rate 1, but then looking at or observing that process at the clock capital lambda, where capital lambda is given by this. So therefore given every locally integrable function little lambda, you can construct a non-homogeneous Poisson process with that as intensity function by starting with a homogeneous Poisson process with rate lambda. The next question is, we have just seen that any non-homogeneous Poisson process arises as a time change of homogeneous Poisson process. This raises the reverse question. Given a non-homogeneous Poisson process, is it possible to revert back to the underlying homogeneous process where the non-homogeneous process presumably came from? Clearly this would require an inverse time change, and that may not always be possible. So when is it possible? Here is the result. Let n tilde t be a non-homogeneous Poisson process with intensity function lambda. Assume that the following properties hold, namely lambda's t is strictly positive for all t strictly positive, and the integral from 0 to infinity lambda t dt is infinite. That means even though lambda may be locally integrable, but the total integral of lambda from 0 to infinity is infinite. So that the function capital lambda t, if you define it this way, this would be strictly increasing. Capital lambda t equal to 0 to t, little lambda s ds would be strictly increasing because lambda is assumed to be strictly positive. So integral of a strictly positive function as t increases would keep on strictly increasing. It is certainly continuous, basic theorem of calculus, and it will be a continuous function on 0 to infinity onto 0 to infinity because of this assumption that integral 0 to infinity lambda t dt is infinite, and therefore if you let t go to infinity in the integral 0 to t, your integral 0 to t lambda s ds as t goes to infinity goes to infinity. So therefore every positive real number is exhausted as a value of capital lambda, and therefore if it is continuous strictly increasing onto, it has an inverse function, lambda inverse. So now you look at the process nt, which is n tilde. Remember, we started with a non-homogeneous n tilde process. Look at n tilde process at time lambda inverse of t, call that nt. Then one can easily see that this is a homogeneous Poisson process with rate lambda. I'll leave the details, and the given, the one that you started with, namely n tilde t, is nothing but the lambda, capital lambda time change of this homogeneous Poisson process n. Here's an example of going from what we just said, going from a non-homogeneous Poisson process to a Poisson process with rate lambda by an inverse time change. So let n tilde t be a non-homogeneous Poisson process with intensity function lambda t equal to t. Then you look at the time change process, nt equal to n tilde evaluated at root 2t. You can easily show that that is a homogeneous Poisson process with rate lambda, and of course the original n tilde can be obtained from this n by again making an inverse time change, which is n tilde t is n at t square by 2. So this is sort of how one can get a non-homogeneous Poisson process from a homogeneous Poisson process back and forth by time change or inverse time change. Time change is always possible, inverse time change may not always be possible unless the intensity function of the given non-homogeneous process satisfies certain conditions. Okay, now we are going to describe another very, very important and practically very important way of how a non-homogeneous Poisson process may arise out of a homogeneous process. This is a very important and useful idea. This is called sampling or classifying of pp lambda. Start with a homogeneous Poisson process nt with intensity lambda. Suppose there is a device that records and notices the intervals. If at the time of an arrival the device fails to work for some reason, then that arrival will not be recorded or noticed. So you have a Poisson process, homogeneous Poisson process with intensity lambda. Accordingly, there are arrivals coming at random points of time, but not all arrivals need to be recorded. If the recording device is down or fails to work for some reason, at the time when an arrival occurs, that particular arrival may not even be recorded. So now an assumption, suppose for each arrival there is a probability p, it's a constant probability p that is recorded, and of course probability q equal to 1 minus p, that it goes unnoticed, independently of the time of the arrival and of all other arrivals. And now let n1t denote the number of recorded arrivals and n2t the number of unrecorded arrivals up to and including time t. Notice that if all arrivals were recorded, that means p is 1, then of course n1t is same as the original nt, all recorded arrivals same as all arrivals. But in case p is not equal to 1, there is a possibility that not all arrivals would be recorded, and therefore n1t may not be equal to nt. However, one thing is clear, both n1t and n2t are counting processes, should be clear from the definition, because one is a number of recorded arrivals and the other is a number of unrecorded arrivals up to time t, so they are both counting processes. And moreover, the original nt process is the sum of n1t plus n2t. That's clear, because up to time t the total number of arrivals must be the number of recorded arrivals up to time t plus the number of unrecorded arrivals. This was about what is called sampling or recording. There is another thing that we are going to get to, but before that, so through sampling or recording of a homogeneous Poisson process, we got two counting processes, N1t, N2t, whose sum is the original process Nt. It turns out that these two counting processes, N1t and N2t, are two independent homogeneous Poisson processes with intensities lambda p and lambda q respectively. We'll prove that later. More generally, now comes classification. Why only recorded and unrecorded? Suppose each event and occurrence or occurrence in a Poisson process homogeneous with intensity lambda can be one of k different types. Earlier it was two different types, recorded, unrecorded. But now suppose that each arrival can be one of k different types with probabilities p1, p2, pk independently of the time of the occurrence and of everything else. Here of course p1, p2, pk are probabilities, so they are numbers, non-negative, which add up to 1. So every arrival has to be one of these k types. Suppose I denote for every I from 1 through k, nit is a number of type I events up to and including time t, then one can show that these nits for I equal to 1 to k are k distinct processes. They are counting processes and so on and so forth, and they add up to nt. The sum of these k processes at any t is nt. It turns out that these k counting processes are themselves k independent homogeneous Poisson processes with intensities lambda p1, lambda p2, etc., lambda pk respectively. The previous case, often referred to as sampling from a Poisson process, is clearly a special case with k equal to 2. There are only two types, recorded or unrecorded. Essentially, a homogeneous Poisson process is being broken up into more than one independent homogeneous Poisson processes in both cases. We will later consider a much more general decomposition, which is why it's not proved here, where a homogeneous Poisson process with intensity lambda will be broken up into independent Poisson processes which may actually be even non-homogeneous. So here what we saw were something where a homogeneous Poisson process is broken up into independent two or k many independent processes which are going to be shown to be actually homogeneous, independent homogeneous Poisson processes. But later on we will have a mechanism or see this general decomposition where the component processes into which the homogeneous Poisson process is being decomposed may actually even sometimes be non-homogeneous. This will be achieved by sampling from a homogeneous Poisson process with rate lambda or by classifying events of a pp lambda where, unlike what we assumed just now, the probability of an arrival being recorded or being classified into different types may be allowed to depend on the time of that arrival. In both the earlier cases we said an arrival is recorded with probability p irrespective of the time of arrival or classified into type I with probability pi irrespective of the time of arrival, but in a more general model we will assume that the probability of an arrival being recorded or being classified into different types may be allowed to depend on the time of that arrival. But independence of other arrivals would be retained. Of course, the above results, above special cases would just be the special cases of this where the probabilities do not depend on the time of that arrival. So as promised, we were actually able to show how exactly or precisely by making a time change. First of all, we explained what is meant by a time change, and by making a time change starting with a homogeneous Poisson process, how we can arrive at non-homogeneous Poisson processes with different intensities. In fact, given any intensity function, that means any function of positive reals taking positive real numbers, positive real values, as long as it's locally integrable, then we can always construct a non-homogeneous Poisson process with that intensity function by this method of time change starting from a homogeneous Poisson process. We also examined the issue of when is it possible that you start with a non-homogeneous Poisson process and presumably it appeared from some homogeneous Poisson process. Is it possible to revert back to the homogeneous Poisson process? Now, in general, it may not be always possible because this requires an inverse time change, but we give conditions as to when it is possible to go back from the non-homogeneous Poisson process to an underlying homogeneous Poisson process from which this non-homogeneous Poisson process may have been obtained. But then towards the end, we also just introduced another idea which we are going to explore later on, and that idea is that of what is sometimes called sampling from a homogeneous Poisson process. It also can be classification of arrivals of a homogeneous Poisson process. So here in this module we had just talked about sampling with fixed probabilities or classifications with fixed probabilities, in the sense that we have a homogeneous Poisson process, but only certain arrivals would be recorded or sampled, others would not be recorded or not sampled with a fixed probability, independent of the time of arrival and independent of all other arrivals. Or it could be that each arrival could be of type 1 or type 2 or type k with fixed probabilities p1, p2, pk, independently of the time of that arrival or any other arrivals. So this of course decomposes the original process, original homogeneous Poisson process, into a number of counting processes. We are eventually going to show that these component individual processes themselves turn out to be independent Poisson processes, sometimes homogeneous and sometimes possibly non-homogeneous. So that will be our next task.